Hi everybody, welcome to our extra example for drawing shear and moment diagrams using the graphical method. And this example was included because it does have a beam that has an externally applied moment, and we want to see how that affects the moment diagram. Further, because it's fixed, at the end there'll also be an externally applied moment that is a support reaction that comes when we do the statics. And so I've already provided the free body diagram with the support reactions. And it's really important for this one that we look at the sign conventions for drawing shear and moment diagrams, or just the sign conventions for shear and moment. And so if we look over to the right side of the page, I've included the positive sign conventions, and you can see that moments that cause the beam to smile are considered positive. Shears that cause the beam to rotate clockwise are considered positive. And so let's see what that's going to do for us in drawing our shear and moment diagram. So we're going to start with the shear, as usual. And again, I'll say this every time, be consistent. Label your diagram so people know what you're drawing. And so we're going to jump down by the 130 kilonewtons. Remember that 60 kilonewtons per meters that's going upwards, it's not going to affect that 130 because right where the 130 is applied, we have moved over 0 meters. So we have 0 times the 60 kilonewtons per meter. So it doesn't change the 130. Once we go over a millimeter, it would start to change it. So we're going to drop down to our negative 130. And then we can see that we have a constant load for the next 3 meters. So we can mark that, just indicating where we're going to see our next big change on our shear diagram. And we know that the change in the shear is going to be caused by the area under the load diagram. And so we have our negative 130 plus our 60 times 3, and that's going to give us 50. So we're going to jump up to positive 50, and because the shear, the slope of the shear is equal to the load, we know that since we have a constant load, we're going to have a constant slope on our shear. And let's hope I can get a nice straight line that connects those two. Sweet. Okay, so then if I move over 1 meter, I can see that I have an applied moment, but that moment doesn't change the shear diagram. That moment does affect the reaction, that 130. If that 140 wasn't applied, the 130 reaction would be different, and so that's where it does come in and sort of change the shear diagram, but we don't see a direct jump or anything on our shear diagram due to an applied moment. So really, we're just going to go straight across to the 1 meter and say, okay, nothing's going to change there, and so we'll just keep going straight across until we get to our applied 50 kilonewtons, and then we're going to drop down. So we have our shear diagram. And we can see on here that the absolute maximum shear, we can say absolute value, is going to be equal to 130 kilonewtons. So we can get that right off of our shear diagram. And we're going to want to find now our moment diagram, and we can see that we're going to need to find the area of a triangle, but before we can find the area of that triangle, we're going to need to know what this distance x is. Now remember, we can actually find x easily simply by taking the height of the triangle, which would be 130, and dividing that by the load that changed us, or the rate that we were changing, which was 60 newtons every meter. So if we divide that by our 60 kilonewtons per meter, and that 130 had kilonewtons on it, and we don't have to worry about a sign because we're talking about distances here, what we end up with is 2.17 meters. So we now know the length of that triangle, so we know that area 1 would simply be equal to, now we can include the negative because we want to remember we have negative shear. We'd have our negative 130 times our 2.17, and then of course times a half because it is a triangle, and we're going to find that we have an area equal to negative 140.8. So now we're ready to draw our moment diagram. So again, let's just label everything so it's nice and neat so anybody else could look at what we're working on and know what we have going. So the first thing we need to do is we actually have this externally applied moment. And just like if a point load causes a jump on the shear diagram, an applied moment causes a jump on the moment diagram. But we need to know which way to jump. And so if we look back over at our sign convention, we're starting our moment diagram on the left end of the beam. So we're going to always use the sign convention reference as if we're looking on the left side of the beam. And so if we look at our sign convention, a moment that's going counterclockwise, we said, is negative if it's on the left side of the beam. So that means we're going to drop down negative 120 kilonewton meters. And then we've already figured out our area 1, and so we can bring down where that area, approximately where it hits, just to sort of help us out. And while we're at it, I'll bring down where the end of the triangular shapes go, the positive triangular. We can bring down the 1 meter mark, and then finally the end of the beam. And so we know we have area 1, we know it's a negative 140, so we're going to subtract that from the negative 120, or I guess add it to it. So we're going to end up somewhere down here at about negative 260.8, but we need to talk about how are we going to get down there. Are we having a increasing slope or a decreasing slope? So this would be decreasing, there would be increasing. So which way do we want to curve that line? So if we look back at our shear, we can see that the magnitude of the shear that we're adding gets less and less every meter that we go over. And since the slope of the moment diagram is equal to the shear, if the magnitude of the shear is decreasing, then our slope should be decreasing. And so we can draw this with a decreasing slope. And again, if it helps you to imagine decreasing, don't forget that you can draw your little person, say they're hiking down the hill, and so the slope would be getting easier and easier as they approach the 260. Now we need to look at what happens from now the positive area that we have. So we have this A2, and so we can calculate the area of A2. It's going to be a triangle, so we'll have our 1/2. It's 50 tall, and it's the leftover distance of the 3 meters, so it would be the 0.83. And that's going to turn out to just be 20.75, but that is positive, so that's going to increase our moment and bring us up a little bit. Not very far. We're going to come up just a small bit. So we're going to be somewhere around 240, still 0.05 now. We'll go ahead and carry about a little bit of extra sig figs just so we don't have a lot of round off. And in this case, what's the shear doing? Is the shear getting bigger as we move to the right or getting smaller? It's increasing. We're adding more as we move to the right, so our slope will be increasing, so we're going to have an increasing slope. Then we have what looks like could be a solid area, but don't forget, we actually have an applied moment that's going to cause a jump. So we need to look at area 3 and area 4, which fortunately for us are the same as far as magnitude. So area 3 equals area 4, which just equals to 50 times 1. So we have equals to 50 positive that we're going to be adding to our beam. And so we can move over, or adding to our moment diagram. So we can move over and we can increase by 50, which would take us up to positive, or I'm sorry, still negative. It's a negative 240 there, up to negative 190. And this time it's a linear, that should be a nice straight slope. Increase because the shear is constant, so our slope is constant. Now we have this applied moment. And the applied 140 kilonewton meters, well, that's rotating clockwise. But do we call that positive or negative? Remember I said earlier that since we're starting at the left side of the beam, we're going to use the left side of the beam as our reference for direction, because that's where we started our moment diagram, is from the left. So all sign conventions start on the left side. So on the left side of the beam, a clockwise moment is positive. So that means we are going to jump by 140. So we'll just jump up. So we would be at minus 50.05. And then we have another 50 to go up by that's left in our last area 4. So again, that's constant. So we're going to see a constant slope, and that basically takes us to 0. We could say it's not quite 0, but really it's basically 0. It's 0.05. So we close. So here's our moment diagram. And from this, we can see that we have our maximum moment, and again, it's going to be absolute value, but our maximum moment is going to be equal to 260.8 kilonewton meters, or with appropriate sig figs, 261 kilonewton meters. So I hope that helps you figure out how to draw moment diagrams when you have applied moments. Pay attention, if we start on the left side, to the direction on the left end that's positive or negative for a moment. Good luck on your homework.